Hey, this is your stats sensei, Mr. Spensei, looking to go over some confidence intervals. We're going to review the concept of confidence intervals very rapidly and do confidence intervals for one sample proportions. Hope you'll find this useful. So remember, the purpose of a confidence interval is to estimate a range. So this is estimating a range of where the true population parameter falls. And it's always the estimate plus or minus the margin of error. Okay, so everything after the plus or minus is a margin of error. Also, all confidence intervals are two-tailed, all right? And alpha is the combined area in the tail. Very important that you know this. As we increase the level of confidence, margin of error or the width will increase. So if we increase the confidence level, the interval width will increase, as will the margin of error. As we increase alpha, the margin of error and our confidence decreases, the interval width gets smaller, all right? Because there's more area in the tails, and more area in the tails means our interval width gets smaller. As we increase the sample size, the margin of error decreases. As we increase the standard deviation, the margin of error will increase. I should also say this about this other one. As we increase the sample size, the margin of error decreases and the standard error also decreases. So as we increase the sample size, the margin of error decreases and the standard error decreases. Because we only have sample data, we are never able to say that what the exact population proportion or mean is. We can claim with a certain level of confidence where we believe it to be located, all right? So when we were working with means, we had X bar plus or minus T star S divided by the square root of N, and everything after the plus or minus was a margin of error, and this part was the standard error. Well, similarly, everything after the plus or minus is the margin of error, and this part that I just circled is the standard error. All right. Notice we have a change here on our formula. When we were working with the hypothesis test, we were using the true population proportion. We were using P, the true population proportion, and we were using it here. But here we have P hat and Q hat. And the question should be asked, well, why? Why the difference? Well, remember, here we had some claim that P equaled. And because we had a claim, we could use it. Here we're trying to make an estimate, so we don't know. We have no claim, we're estimating it, and we're estimating it using P hat. And remember, P hat is the sample proportion. All right, P hat is the best estimate, and it's the sample proportion. Remember, the z-score tells you how many standard deviations we need to be in order to exceed to have a certain level of confidence. Okay, and there's certain things we can claim. We can claim that we are 95% confident the true population proportion lies within the interval. We can claim 95% of the intervals collected by this method will capture the true population proportion. That's like saying in repeated sampling. We cannot combine those two claims together. So please do not combine them. We are 95% confident the true population proportion lies within the interval, or in repeated sampling, we expect our method to capture the true population proportion. We cannot claim that 95% of the values lie within the interval. We cannot say that there's a 95% chance that a randomly selected value will lie within the interval. We cannot say that 95% of samples result in this interval. And we cannot say 95%. We hate the word probability. We like to use confidence that the true population proportion lies within the interval. So you need to make sure that you know these. Very, very important. Not going to have to recite them, but I'm going to have to recognize them. And we'll have an opportunity to do that here in just a moment. All right. And again, the purpose of the interval is to provide a range of values for the parameter. All right. In other words, we're looking to estimate, in this case, P, but prior to that, we were looking to estimate mu. We're estimating the population parameter, and we're giving a range of values. Okay. All right, so we're going to look at a couple of multiple choice type questions. Please remember, as a concept, please remember that although the population does not change, every sample is different, which means there's sample variation every time we take one. And we'll have a different mean or a different standard deviation or a different population proportion for every single one of them. And our standard errors will vary because of sampling error, not because we did anything wrong. As a consequence, every confidence interval will have a different point estimator. Please remember the point estimator is X bar for means, P hat for proportions, and different endpoints. We do not have any confidence in the endpoints. We are confident in the method and believe a given level of confidence that we will capture the true population proportion. We only make claims about the population. We never make claims about the sample because we know all of the values of the sample. So we make claims about the population. We know the sample. We know the sample. So we're making claims about the population. This is what we're estimating. We're estimating P if it's proportions. We're estimating mu if it's means. There's no estimate for X bar and P hat. We know them. All right. So here we go. To determine the average spent on entertainment during a year in college, a simple random sample of 35 students is interviewed, showing a mean of $825 with a standard deviation of 240. Which of the following is the best interpretation of a 90% confidence interval estimate for the average spent on during a year in college? 90% of college students between this. No, we are 90% confident. We cannot say that. As a matter of fact, 90% of college students spend a mean. No. And by the way, this doesn't even have the word mean, so this is clearly wrong. This does have the word mean, but it's not 90% of college students. We're 90% confident. So this is wrong. So here we start off with, we are 90% confident. Yay, that starts off correctly. That college students spend between this. We have no confidence in the endpoints, and we should be talking about the mean, and that doesn't do that. So that's wrong. We are 90% confident that college students spend a mean. I'd like this to say true population mean, but spend a mean dollar amount between this and this. So on average, we are 90% confident that they spend between this. This looks like a pretty good possibility. We'll keep it as a possibility. We are 90% confident that the chosen sample, oh, wait a second. We're talking about the sample. We do not talk about the sample, we talk about the population. We're making claims about the population. So the only one that could be right is D. For number 2, a planning board in Elm County is interested in estimating the proportion of its residents that are in favor of offering incentives to high-tech industries to build plants in that county. A random sample of Elm County residents was selected. All of the residents were asked, are you in favor of offering incentives to high-tech industries to build plants? The 95% confidence interval for the proportion of residents was calculated to be 0.54 plus or minus 0.05. So they're telling me my margin of error, because remember, margin of error is anything after the plus or minus. My margin of error equals 0.05. And in this case, we're going to say, well, my margin of error is 0.05. And if I did my interval, this would be 0.49, because that's 0.54 minus the 0.05. And 0.54 plus the 0.05 gives me 0.59. So there's my lower bound and upper bound, and we're 95% confident that the true population mean lies within this. So at the 95% confidence level, I like this. The estimate of 0.54 is within 0.05. Oh, that's the definition of margin of error. Margin of error is how far you might be from the population parameter, all right? Or how far the population parameter is from your sample. So in this case, that looks really good. Let's see if we have anything else. At the 95% confidence level, the majority of area residents are in favor. No, we can't say that, because it could be 49% are in favor as opposed to the majority. Majority would be 50% or more. Had this both been 50%, 50 to 59, then we could have said that that was true. In repeated sampling, 95% of sample proportions will fall within this interval. We have no confidence in the endpoints. We are 95% confident that the true population lies within this. By the way, this talks about samples, so that's clearly wrong. In repeated sampling, the true proportion of county residents in favor of offering incentives to high tech will fall within the interval. We have no confidence in the endpoints. All right, and also in repeated sampling, they combine the two phrases together. It's in repeated sampling, we believe this method will capture it, or we are 95% confident that it lies within this. We cannot combine the two, so this is also wrong. Never combine them. In repeated sampling, 95% of the time, the true proportion of county residents in favor will be equal to 0.54. No, we can't make the claim that it's equal to a value. We're just claiming that our method in repeated sampling will capture it 95% of the time. All right, so that's wrong. The only possibility was saying that the margin of error is within 0.05. And they told us the margin of error when they gave us the formula. They gave us the answer right there. All right, so looking at the recipe card. As before, when we were doing high confidence intervals, we have to define our parameter. We have to write our conditions, which we already said with a hypothesis with simple random sample. Our sample size needs to be less than 10% of the population. This is to maintain independence when we are sampling without replacement. Technically, it's not independent because this is a giant M&Ms and the probabilities do change slightly, but we say it's independent enough. And then this is our normality condition, all right? Our sample must be large enough. For means, for X bar is greater than or equal to 30. For proportions, we're using NP and NQ must be greater than 10. This is our sample proportion, plus or minus Z star, P hat, Q hat, and N. Nice thing when we're working with Z star, no degrees of freedom. All right, everything runs the same way as when we were doing the Z test. And our conclusion is the same, except now we're talking about the population proportion. So let's go ahead and run this thing. We're going to actually go back to the same scenario on the unions that we used for the hypothesis test. So when we were doing the unions, we said the local news has taken a simple random sample, very important, very useful, and found that 87 of the 125 union members said they will strike, calculate a 95% confidence level, and provide a conclusion. All right, so what we claimed initially was if we were doing the null and alternative, we would have said P is equal to 75%. The alternative is P is less than 75%. This is optional, not required for a confidence. So you don't have to do this for confidence interval. You do have to say P is the true population proportion of union members who will strike. Conditions, random sample. They told us they took a simple random sample. They said there's 125 of them. I believe that there's at least 1,250 union members. The number of people who said there were strike was 87, that's greater than 10. And the 38 would be our Q, which is 125 minus 87 equals 38. So both of those are greater than 10. So since both conditions are met, the sample is large enough to use the normal approximation. And that's the phrase we need to use. This is the phrase we need to use. All right, so we're going to go ahead and write our formula. P hat plus or minus Z star, P hat, Q hat over N. Make sure you have your hats in there because we are using sample because we don't have a claim. There's nowhere up here in this, nowhere up here do they say that it's 75%. All right, there is no claim. So we have to use the sample. We will always use the sample data for confidence intervals. So stat, test, and I need to scroll down to one proportion Z interval, all right, which is a letter A. I'll do that again. Stat, test, scroll down to letter A, one proportion Z interval. We had 87 who said they were going to strike out of 125. These must be whole numbers. They cannot be decimals. They have to be whole numbers. If for some reason you end up in a situation where you calculated an X and it was a decimal, round up or round down like you learned in elementary, but please make sure that that's what that is. And then we said we wanted to calculate a 95% confidence interval, so 0.95. And there's our values. So where did this come from? I didn't see this. Well, this came from, this is p hat, which equals 87 over 125, and we need to show that work. And I showed that up here. So please make sure you do that. All right. We'll come back to T star in a moment, Z star in a moment, because remember, we're using a Z because all proportions work with a Z. There's my p hat, and q hat equals 1 minus p hat. So this is 1 minus the 0.696, and that goes right there. So how did I get the Z star? Second vars, inverse norm, parenthesis, 1 minus 0.95, close parenthesis, divided by 2, mean is 0, standard deviation of 1. And there, I did that again. Sorry about that. Second vars, inverse norm, 1 minus 0.95 divided by 2. Since this is a Z-score, all Z-scores have a mean of 0 and a standard deviation of 1. And we end up getting 1.96. So 1.96 is the number of standard deviations. And when we ran the test, this was my lower bound and this is my upper bound. So we are 95% confident that the true population proportion of union members who will strike lies within this interval. Because 75% lies within interval, we do not have sufficient evidence to dismiss the claim that the union members will strike. All right, because remember in the initial problem that we did on the previous video, we said that there's 75%, so we can't ignore the claim. It's plausible. It lies within interval. And in repeated sampling, we expect that this method will capture the true population proportion of union members who will strike 95% of the time. All right, that's the introduction to sample proportions. I thank you for hanging out with your stat sensei. Talk to you later.